In this talk, I will be discussing subtyping, covariance, and contravariance. Specifically, as it applies to functional programming. The usual definitions and discussions of subtyping are heavily influenced by object-oriented programming. In object-oriented programming, subtyping is usually understood as that of object-oriented inheritance. If one class inherits from another class, then the second class is a subtype of the first one. And usual discussions of subtyping are related to the so-called Liskov substitution principle. But the discussions are so complicated and not clear that I never understood them. I'm not sure that anybody really understands them in the object-oriented community and at the level of mathematical statements. So there's a lot of discussion, but that discussion is usually not rigorous. I would like to avoid that, and so I'd like to take a look at what is usually understood under subtyping in object-oriented programming. So suppose you have some program. Then you declare some value. I will use Scala syntax for that, but it doesn't really matter. So I'll say there is some x, and this is some class, let's call it C. So I create a value of class C. Then there is some code, and then I call some methods for this x. So this is what is usually done, is to say, okay, let's suppose that we have another class D, which is a subtype of C. And then they say, you should be able to use this value y instead of x everywhere. Well, that's what they say usually when they discuss subtyping in object-oriented programming. And the Liskov substitution principle says that it should give the same results, or it should be equivalent, or something like this, but it's never clear what exactly that is. But from a programmer's point of view, it looks like you should be able to replace this first program by a second program where instead of x you use y, but you use exactly the same code as before, just you call it y instead of x. And the program should work in the same way. They say that's impossible, but probably it's at least it's going to compile, let's say. So let's make it in a different, let's make it weaker, right? So we don't talk about the program prime being exactly the same or equivalent to program, but that is impossible because actually object-oriented programming uses subtyping to change the behavior. So you can use this y instead of x in the sense that the program will compile, but actually you do that because y has a different behavior than x. And so, for example, let's suppose that C is some kind of printer interface and D is a very specific printer implementation, the printer that you want. And so clearly the new program will have a different behavior. It will print to the printer you want and not to some generic printer. So the results are not going to be the same. But so let's not talk therefore about the new program being equivalent to the old one, or that you should be getting the same results as before with the new class. But instead, let's just say the new program should compile. The compiler should accept that the code that you had before with X now is written with a different value, a different type. The compiler should accept that. Okay, so subtyping means, so if C is a supertype of D and D is a subtype of C, so let's write it like that, where C is a supertype of D. If that is true, then the compiler accepts, so f of y compiles. The compiler accepts that we use values of one type instead of values of another type, even though the function f was declared to have a type, let's say c to some x, and not d to x, but the compiler accepts that this is a valid program. So let's take that as a definition of subtyping. A type D is a subtype of C if the compiler will accept applying a function f of type c to x with the argument of type c to a value of type d. So we are able to write f of y. All right, so this is going to be our definition of subtyping. Now, what follows from that definition, in particular, in terms of functional programming? In functional programming, we think more about types than values and how to organize mutation or something like that, or methods like getters and setters. We don't think about that as functional programming. We usually just think about values. So what does it mean? Well, that D is a subtype of C if f c to x can be applied to arguments of type D. Now, what does it mean? It means, right away, let's take this function f of type C to C as the identity function. We are then allowed to apply f to argument of type D. So let y be a value of type D. Let's compute f of y. What would that be? Well, that would be a value of type C. So automatically we get a function which I will call convert CD, which converts C to D. So it converts a type to its supertype. So from this point of view, a subtyping relation between types C and D means that there exists a function that converts C to D. And this function is automatic. The compiler substitutes that function into the code behind the scenes. We don't have this function explicitly in our code. We see that this is actually equivalent to the definition of subtyping that I wrote. If there exists this function, which is automatically substituted by the compiler, anytime that we apply a function with argument of type C to a argument of type D, the compiler will automatically insert that function. So this is actually a very good definition because it's much more specific. It can be used to ask, well, what is this function? Let's look at this function. What does it do? What are different kinds of this function that a particular language allows? Because every language defines subtyping in a different way and allows certain types to be subtypes of others. The programmer cannot define arbitrarily, say, that type, tuple of int and string should be a subtype of array of byte or something. That makes no sense. But actually, Scala will not allow you to do this. There's no syntax for saying an arbitrary type A should now be considered a subtype of an arbitrary type B automatically. Scala, however, can declare implicit conversion functions. And so actually, if you want to do something like this, you could declare an implicit conversion from whatever you want to whatever you want. And once you declare that, and once that implicit is in scope, you will get the behavior of subtyping, as if you had that. So actually, Scala allows you to have arbitrary subtyping in this sense. Well, do you want to use it like that? Probably not, because that will be very confusing. Suddenly, this function is magically inserted in places that you don't necessarily expect. But that's what follows from the weakest definition of subtyping that we can get. Now, why is it that object-oriented subtyping talks about behavior, that the behavior of a subtype must be a subset of a behavior of a supertype or something like this? It's because object-oriented programming does not use coproduct types in the context of subtyping, but functional programming and languages like Scala do use that. So let me talk about this. Coproduct subtype. Now this is something that Scala programmers are very familiar with. We have code like this, sealed trait T, and then final case class T1, whatever it's in there, extends T, and then final case class T2, whatever, extends T. So that is an implementation of a coproduct where a value of type T could be T1 or T2. And usually we write code where we use pattern matching. Now, object-oriented programming does not use this kind of pattern very much. It probably could be implemented in some way, but the syntax for this in Java is still not there. The pattern matching is still very limited in Java, but it could be implemented in any object-oriented language that has runtime type information. For example, you could say you take this argument T and you detect its runtime type and you check if it's T1. So you try a class cast or something like this. And if that succeeds, then you have a T1 and then you cast it and then get the variables out of it. If it does not succeed, then you try casting to T2 and so on. Now this can be done, but it is long and difficult to write every time. So it's not convenient. People don't do it. But the result is that the object-oriented community doesn't think of T1 and T2 as subtypes of T. This pattern is not very well known in there. And so, but if it did, then it would completely violate their usual reasoning of subtyping, because T1 and T2 can be completely different. They are not extending the behavior of T in any way. There is no behavior of T other than it's either T1 or T2. And so actually, this situation is very different from the subtyping that object-oriented programmers are familiar with. And that, you could call it product subtyping. Where you say that product of AB is a subtype of A, or a product of ABC is a subtype of AB, or something like this. Now, when product subtyping is used, the subtype has more information than the supertype. And when the coproduct subtyping is used, and the subtype has less information than the supertype. So the supertype T is either T1 or T2. It has strictly more information than T1 and strictly more than just T2. Whereas in product subtyping, it's the opposite. So the object-oriented community focuses on this product subtyping, where the subtype is a class that has more fields, more methods, and so on. And that's what they usually talk about. And then it makes sense to say, well, the behavior of those fields must be the same as in the supertype, but there are some more fields and some more methods that shouldn't modify the existing behavior and so on. But now, in the functional programming language, none of this can be discussed because they're just types and values. There's no behavior in these types and values that you can, behavior in object-oriented language. Usually it means modification and methods that modify things under certain conditions. So none of that is applicable to functional programming. And so in particular, the Liskov substitution principle is trivially satisfied always. So we don't really even discuss it in functional programming. So now this is a point where I'd like to say that this coproduct subtyping and the product subtyping are central to functional programming in Scala. Both are used. They can be mixed so that you can have subtyping that's neither this nor that, because you can say you can have a pair of a coproduct type and a product type, and that's going to be a subtype of something else. So let's say a pair of T1 and this AB is a subtype of a pair of T and A. And now that is neither coproduct nor product. So the subtype has neither more information than the supertype nor less. It's no longer useful to talk about that and to always assume that the supertype has more information than subtype, or that the supertype has less information than subtype. Is no longer the case. So generally, subtyping can be anything. And there's also function subtyping in functional programming, which is that a function A to B as a type is a subtype of C to D as a type if B is a subtype of D and C is a subtype of A. So there's opposite directions of subtyping that are necessary for this to happen. Now, how do we show that this is true? Well, we can actually show that this is true by demonstrating a conversion function. So now I'm going to talk a little bit about this. So if we define subtyping via conversion function, then in order to demonstrate subtyping, we just need to show what the conversion function is. And then we demonstrated the subtyping. So what is the conversion function for this case? It's just a function that takes t1 and returns a value of type t. But t1 in Scala is already of type t. So that function is just an identity function that reassigns the type. Let's call it, let's write code for it just to make sure we understand what happens. So it's a t1 to t. And that's a function that takes x of t1 and returns x. It's an identity function. But because we reassign the types, it's a conversion function. Now, in the product subtyping, you would have to drop some values. You can convert a value of type ABC to a value of type AB by just dropping C. But if you used object-oriented inheritance for that, then you don't drop it. You just reassign the type again, just like we did here. In the function subtyping, however, you have to write some code for the conversion function. So that is not going to be automatic. Now, but that code is, of course, easy to write. A to B to C to D. All right. So it's going to be some function f of type A to B. And that's going to be, I should put parentheses here just to be consistent. So that is going to go into a function from C to D, right? I should write double arrows here to be consistent with Scala syntax. Let me do that. So how do we define that function? Here in this code, we need to define a value of type D that we return. And that value is essentially f of, now we need an A. Instead of A, we have a conversion from C. And then we convert that from B to D. So you see, we put the conversions in this way, and then we have those conversions from C to A, from B to D, because by assumption, these are subtyping relations. And then we define the subtyping relation for the function. So in this way, we can see that functional programming has richer subtyping relations than object-oriented programming, because in particular, it uses the coproduct and the function subtyping. Now, let me talk about how we define covariance and contravariance, and how they're related to subtyping. Just as with subtyping, tutorials about covariance and contravariance that I have seen are confusing and not clear. It's not clear what happens and when is something covariant and when is something contravariant. I'll explain in a different way what happens, and it will become more clear. So if we define a type constructor, so first of all, covariance and contravariance are concepts that require type constructors. So we talk about if a type constructor is covariant or contravariant. Cannot say, is this function covariant or is this number covariant? That makes no sense. It's always a type constructor. So let's say we have a type constructor. In Scala, I would write it like this. Let's say this is either of A to int to A, and then tuple of A Boolean. Okay, well, it's whatever comes to my mind, I can just write a type expression, and that will be a type constructor. Or it will be another way of defining a type constructor is to define a class with a type parameter. And then it can have some methods, values. Let's say it's an abstract class. It can have some definitions, whatever I want. So in this way, in Scala, we define type constructors, either as a type alias or as a trait, an abstract class, or something like that. Or it could be a case class. So the question is, what is covariance and contravariance for type constructors? And the first question is this F here, is this covariant or not? And the usual answer from tutorials that I have seen is that you need a type annotation to show that it is covariant. So you write type F of plus A or something like that, or you write trait G of plus A, and then it becomes covariant. And if you write minus A, then it becomes contravariant. Now that is wrong. Actually, the type constructor itself is covariant or contravariant or neither, regardless of any type annotations. The type annotations that you use here for plus or minus do not make it covariant or contravariant. They cannot, because it already has by its own type expression that property. And in fact, both of F and G that I wrote right here are covariant. And if you try to write minus in your code instead of plus, there will be a type error. The compiler will not accept that they're contravariant because they cannot be contravariant. They are already covariant. The only thing that you achieve when you write a type annotation like this is that the subtyping feature will be turned on in the compiler. That's actually the reason why you want to use those type annotations, not because you want to make it covariant. You cannot make a type constructor covariant if it wasn't already. So, and this is clear because if you write the wrong annotation, the compiler will not accept your program. So obviously the compiler already knows if your type constructor is covariant or not. And this annotation serves some other purpose. And that's what I'm saying. The purpose of the annotation is to turn on the subtyping feature in the compiler. What is that feature? The feature is that F of A will be a subtype of F of B if A is a subtype of B. So that is the subtyping feature. So then you would be able to call functions with arguments of type F of A instead of argument of type F of B. That's what it is. That's what it will give you, this annotation plus. But it will not change the nature of the covariance or contravariance of the type constructor itself. Because, like I said, if you try to do it in a different way, the compiler will not accept it. If you try to say that F is contravariant, the compiler will not accept that. But if you do not write the plus here, then the subtyping feature will not be activated in the compiler. And then it will not be automatic that a function of with argument of type F of B could be called on arguments of type F of A. This will not be automatic. That's all it does, this plus. So now that we understand that, the question remains, how do we determine if a type constructor is covariant or contravariant? We determine that by looking at the type expression. Now, here is a type expression that is easier to see. It's just one line, but here it's spread out. And what if we had a more complicated types here? We had some var here, for example. What would be the type expression for that? Now, the var actually is a thing that is difficult to spot, but once you have var, what you actually have is a getter and setter generated for you. And when you have val, you only have a getter generated for you. So you need to think about val and var in these terms when you think about type constructors in Scala. So let's rewrite this code in this way. So there's a get a, there is a def f, and there's a get x, and there's a set x. So yeah, let me get rid of that. So actually this type is going to be rewritten by the compiler into this. And what does this mean? It means essentially a tuple of all these methods. So this is the same as a tuple a function int to a again, and the function a to unit. So that is the type expression that represents this type G, the type constructor G. And this is the type expression that represents the type constructor F. Now, if you squint a little and look at where the type parameter is in these type expressions, you will find that sometimes the type parameter is to the right of a function arrow and sometimes to the left of the function arrow. So the positions to the right are called positive and the positions to the left are called negative. So this is a positive position, this is a positive position, positive position, this is a negative position, this is a positive position, positive. So this entire thing is a negative position, and inside it, A is in a negative position, but negative with negative become positive. So actually this A here is in the positive position. So this is the rule. You just trace the function arrows. Ether and tuple don't change. Covariance and contravariance, they remain positive or negative. But function arrows flip positive to negative. That is the rule. I will explain briefly why that is true. But first, that is what you need to do. So then you look at your type parameter and see what are the positions in which it occurs. So in this case, it only occurs in positive positions. And so then F is covariant. In this case, A occurs here positive and here in a negative position. And so this is neither covariant nor contravariant. The usual term invariant is confusing. I'll explain why. So I don't use that term. I don't want to confuse myself. Unless the type parameter is always in the positive position, your type constructor is not covariant. Unless it's always in the negative position, it is not contravariant. So example of a negative position would be type H of A is A to string. So something like this. Now this A has a negative position because it's behind a single function arrow. And then this H is contravariant. If you want to activate subtyping for it, you would put a minus in here. but you don't have to. It will still be contravariant. So now, what does it mean that it is covariant and contravariant? In light of our definition of subtyping, it means that if A is a subtype of B, so if there is a conversion function of type A to B, then, well, there should be a conversion function of f of A, f of B. Right? Now, if you are familiar with functional programming, you recognize what that is. It is a type signature of map, or fmap, as it is usually called with this type signature. In other words, if you have a function fmap, then you can implement this sort of subtyping, which is the usual formulation of covariance. So the usual formulation of covariance is that type constructor is covariant if you have this subtyping condition. Whenever A is subtype of B, then f of A is subtype of f of B. Now this, if you translate that into clear definitions, it just says that the type constructor f has an fmap method. It can convert one conversion function into another. And we know what that means. When a type constructor has an fmap method, we call it a functor in the functional programming. But this is the same as to say it's a covariant type constructor. The same similarly for contravariant, you use cmap, contramap, which is A to B, f of B to f of A in the opposite order. And that is the usual definition of contravariant subtyping. When A is a subtype of B, then H of B will be a subtype of H of A. Now, we see that if the type constructor has an fmap method, that means it is a covariant, and that means we could use the subtyping in this way. So this is the real connection between contravariance, covariance, and subtyping. And then it remains just to show that whenever the type constructors are to the left of the function arrow, that makes them contravariant. In other words, that makes you able to implement contramap. And if the type parameter is to the right of a function arrow, then it allows you to implement map. Well, that needs to be shown. So that is actually now a very specific question. Implement fmap or cmap for a given type constructor. So that is a very specific task that can be done using code. So you ask how you can write code, for example, for this kind of type constructor. So what code do you write with this type signature? And I'm not going to talk about this. It's a very well-defined task. And actually, this code can be generated automatically from the type expression. Every time you have an A, you need to destructure this, then this is replaced by B. Every time you have an A here, that's replaced by B. This is a function, so it needs to be replaced in the way that I've shown here, where you substitute argument and substitute and convert the function result here and so on. So I'm not going to talk much about this, but this is a very well-defined task which can be done. And you can prove that this can be done. Whenever the type expression is such that the type parameter is always to the right of all function arrows, or always in the positive position, even if it's to the left, then it must be to the left of some other function error like this, then it's also positive. So if your type expression is like this, where your type parameter is always in the positive position, you can prove and generate the code for fmap for that type constructor. Similarly, if your type parameter is always in the negative position, then you can generate the code for cmap from the type expression. What happens when the type is both in positive and negative position? You cannot generate fmap or cmap for that. You can generate another function called xmap, which has a different type signature. So it takes not just A to B, it takes a pair, A to B and B to A, and then it gives you f of A to f of B. So you need, in order to transform f of A to f of B, you need to have both A to B and B to A. Now, clearly, this would not be very well working together with subtyping, because that means A would be a subtype of B and B would be a subtype of A at the same time. But the function xmap by itself doesn't have to do anything with subtyping. Just like fmap and cmap, they don't have to do anything per se with subtyping. They're just functions with these type signatures that satisfy certain laws, and you can show that they exist for type constructors of certain form. And similarly, you can show that this exists for type constructors of a certain form. For example, for type construct this form. And you can generate the code for that and show that all laws always hold. And so this precludes a meaningful use for subtyping, but it doesn't mean that you cannot transform f of A into f of B. You can. And so invariance is a little strange to say that you cannot ever transform f of A into f of B. Yes, you can, but subtyping will not work with this function. So that means for Scala, whenever you have a var of this kind in your class, this makes this class incompatible with subtyping. If you don't have a var, so then if you didn't have this here, then it would be positive everywhere, and then it would be a covariant type constructor. All right, so let me summarize what I have shown here. Type constructors in functional programming are covariant or contravariant or neither. Subtyping in functional programming means conversion functions. So it's important that the property of being contravariant or covariant has nothing to do with subtyping. And subtyping, as a property of types, has nothing to do with covariance and contravariance as such. So you can have subtyping with types that have no type parameters. You can. And for those, covariance and contravariance makes no sense to discuss. And you can have type constructors that are covariant or contravariant in the sense of having these functions. So the definition of covariance and contravariance is just a type constructor is covariant if this function exists that satisfies the laws of fmap. The type constructor is contravariant if this function exists, satisfying the laws. Has nothing to do with subtyping and can be used in languages that don't have subtyping. So this reasoning about type constructors in positive and negative positions is universal for all languages that have types and type parameters and functions. And this reasoning is universal for languages that have subtyping. Don't have to talk about type constructors at all. And then there's a connection between type constructors covariance and subtyping. Covariant type constructors. They naturally support subtyping. Support subtyping. So contravariant also. Covariant or contravariant type constructors naturally support subtyping in the sense that this function fmap or this function cmap can be used directly to create the necessary conversion function for subtyping. So let me add here. The type constructors in FP are covariant or contravariant, understood via fmap or cmap. So the covariance and contravariance is understood as a property of the type constructor that allows us to create a fmap or cmap function for it. Subtyping is understood via conversion functions. Covariant or contravariant type constructors naturally support subtyping. Scala, or Java as well. You need to annotate, require annotations, type annotations to activate the subtyping feature. So the compiler will actively insert those conversion functions, so to speak, behind the scenes. If you don't activate the subtyping feature, then it will not. So the subtyping feature can be turned on and off, but the covariance must be there to begin with, or contravariance. So if covariance or contravariance is not there, then subtyping cannot be turned on and off because covariance and contravariance is required first. So var prevents subtyping to work, prevents it from working. So that because if you have a data structure with a var like this, with this type A, or anything that involves the type parameter A, then this is translated into a getter and a setter, and that will automatically put both in the negative and the positive positions, which will prevent subtyping from working. But it will not prevent you from, of course, using this class or even implementing the xmap function for it specifically. You can do that and use it to transform values, if that's what you want. That concludes my talk.